So for those of you just joining us via recording, we're going to start with working on this problem, which should exercise a little bit of the DTFT machinery, and then probably do another exercise problem, and then move on from there. We actually haven't sent out the slides, but I'll go ahead and send the slides to you guys as well, so you guys can look at them on your own.
Yeah, and in case you're also joining us from recording, the only thing you missed was just us showing the property of the DTFT table, and just like how Cobric generally structures her midterms.
Okay. There you go. And we'll also send this link out if you fill out the sign-in form. Let us know if you have any questions. Feel free to PM us. And we'll just take a couple more minutes here.
Wait, Nico, did you mean DTFT or DFT?
I meant the DTFT.
Okay.
Although you could also, you could try to find the DFT of this signal, but you'd have to choose where to cut it off. So yeah, look for the DTFT. Sorry, guys.
Yeah, I was about to say you didn't give them the N.
Try moving. I just edited it on the Google Docs. See if you move off of the slide and move back onto it if it changes. Do you not change the slides?
Oh, whoops. There.
Okay, it didn't work. Shoot. Oh well. Anyways, guys, so this is the DTFT, not the DFT.
Yes, I could exit the slide and then edit the slide.
Sure.
Okay.
There you go.
There we go. All right. Now we present again.
Hey.
There we go.
Well, I think at that point, seems like probably enough time to at least think about how to approach this problem. Do you guys want to go through this problem? Just say something if you want to, otherwise we'll keep moving forward. Maybe give an emote reaction. I don't know. Chat, anything? No? Cool. We'll move forward from there. This next problem is a similar to the last one. Again, just working through the machinery. Sort of want to get through these a little quickly, so I'll give you guys like 5 minutes. Really just remembering, doing the DTFT. That's really the most important transform for the second midterm, because the DFT is a extension of that. So go ahead and take a couple minutes for this one as well, and then we'll actually start hammering out some good concepts.
Yeah, hopefully you don't get wrecked by this problem, even though there's a rect function here.
That would hurt. One day, Cody. It'll all come back to you.
So when you, I guess when you guys are done with the problem, just emote react.
All right, that's probably a good amount of time to crank through a bit of the problem. So does anyone want to go through this problem? Anyone in particular confused about which transform pairs to use for this? Okay. Okay, I'll spend a quick sec to go through it. So,
Do you
give me
want
1
to
second.
share your screen, Nico?
Yeah, I'll share my screen. I'm also going to turn off my camera because my how my computer works. All right. So the idea behind this guy is that we're going to use the rectangle identity or the rectangle sinc function pair for this one. Give me a second. My computer is terrible. Oh my goodness. Sorry guys, technical difficulties. All right, where are we? There we go. Okay, so, well, first of all, here are the two answers that I just showed up here for the sake of ease of knowing what's what. Let me find my pen. So let's look at what this function is. So we have, correct me if I'm wrong, but we had that x of omega was equal to pi over 2 times the sinc of 6 omega over pi times e to the negative j2 omega. So a couple things are going on here, right? And the idea is that you sort of want to recognize what transform pairs to use. So this right here is from the transform pair that x of omega times e to the negative j2 omega, or the pair that we're going to want to use is the pair that looks like this. right? Or really, if you were to generalize this, you could replace this with some k, you could replace this with some k. And then the pair here that you want to use is the one that looks like this guy right here. Oh, sorry, this is rect. My bad. That the sync, I'll do it from the from one side. So sync of some omega c n over pi n is the same thing as writing rectangle of omega over omega c. Sorry, this is sine, not sync. So these are the two pairs that you're going to use. And from there, you can just go about solving the problem by knowing that, let's see, if we want to get this into the form of rect of omega over omega c, then this right here is going to be omega over pi over 6. So if we want to write out x of n, this would be pi over 2 times this guy right here. So sine of pi by 6 n over pi n. And then, or I should say, and this is x of n before shift. And then we still have to account for this guy right here. So if I were to bring this down here, I could write that this, the actual full x of n, maybe I'll write like x prime of n here, just for ease of understanding, is going to be equal to pi over 2, and then every n gets shifted to n minus 2. So we would get sine of pi by 6 n minus 2 over pi of n minus 2. And if you look up there at the answer, that's the same thing. But now the question becomes, where does this 1/6 come from? That's really just saying, because it's not exactly well defined to, if we leave it discretely at, or if we were to plug in n equals 2 here, we would get a 0 over 0, right? So how do we deal with that? The way we deal with that is we just define it like we would define the actual sync function, which is to say that this is, more formally, pi by 2 times this function up here. So put an arrow up here, and then just 1 or 1/6 technically at n equals 2.
Could also go to the L hospital.
To the what?
Oh, the L hospital, L'Hôpital.
You could also go to the L hospital. That's good. So that's how to do that one. And then we can keep sharing this guy.
Right. Let's share the slides now. Safari unknown. There it is. Okay.
Before we move on from that, any questions there? Cool. All right, let's keep going.
So more DTFT practice. If you feel like just doing the derivatives and using like Wolfram Alpha, go for it. This is from a homework problem I had before.
This one is a little more involved than the last two. It is just using, well, no hints, but it's similar, but it's a little less straightforward, in my opinion. That last one's a good one. Sit back a little. Oh, perfect. That's great. I should also use a Zoom background.
I think Zoom backgrounds make it so that someone walks behind you, like no one notices.
That's true. Currently on a beach, guys. Just chilling, waiting for finals, you know. Oh, my arms don't show up, so I don't look like I'm chilling. It's okay. All right, actually serious. There we go.
Yeah, just let us know when
If you have any questions or
yeah.
you're like, you know, we should just keep going forward. We should like write sketches for this time in between so that they have to fight the distraction of our brilliant comedy.
Dude, that's a good idea.
Yeah.
Yeah, because during exam time they'll be more nervous.
Yeah, exactly. They'll be way less nervous. They'll be like, I don't have someone distracting me.
Lolo.
We're just trying to help you guys in the best way we know possible, which is trying to make you laugh and also trying to help you learn material. Okay, that was about 5 minutes. So this one is a little longer. If anyone wants more time, you can emote react. Otherwise, we'll keep moving forward. The solution for this one is shown up on the screen if you guys are curious about it. Nope. All right, cool.
Okay.
We'll just keep going forward.
So basically the solution, so you start with just the given stuff. You can change the variable. So you change the alpha to a beta. It's just slightly easier to work with. And then you know, you identify what you want. So you just want like this ratio here. And then these are the list of identities or properties of the DTFT that I used. And so you're evaluating the big omega equals 0. So you can evaluate it at the big omega equals 0 because you're looking at the ratio. So you can just pick the point that's most convenient for you because it'll just like it'll be like consistent. So yeah. And then so you can, this is a Parseval here. It's good to use. And so shoot, what was it? Yeah, so you evaluate the second derivative at omega equals 0. And you get this over here. And then you evaluate the first derivative. So we're basically using these properties here. So evaluate the second derivative to get this, and then the first derivative times j to get this. And then you just get the ratio. If that makes sense.
And then you're using Parseval's theorem to determine that you can just take an integral from there and then take the ratio of the integrals.
Oh wait, I don't think you need the integrals. I just have that heat there. But I think the main point is just you.
I mean, that seems right. Yeah, I think you're right.
Yeah, the main point is just you take the first one, then the second one. So the first one corresponds to the bottom, and then the second n squared one corresponds to the top. And then yeah. Does that make sense to everyone? Any questions about the solution?
Let's keep moving.
All right. Okay.
All right. So now we'll go on to a little more conceptual things. One very important part of the discrete time Fourier transform is how it relates to our knowledge of 102, which is that we can, in the same way that we use Fourier series with systems, we can actually use this Fourier transform to describe how a system transforms a signal. More specifically, just that, if you have a signal x of n as an input, y of n as an output, and h of n as the impulse response of the signal, then you can sort of form a similar equivalent as you formed in 102, which is that x of n convolved to h of n is y of n, which means that x of omega in the Fourier domain times h of omega is y of omega. Then so the idea that convolution becomes multiplication. And more explicitly, we can then go on to say that because we transferred over to the Fourier domain, that exponentials are eigenvectors of an LTI system, right? So you can sort of think of, e to the j omega kn is just going to be a delta function in the Fourier domain. So if we were to put that into a system, we would sort of just be pulling out the omega k value of h, of capital H, so h of n in the Fourier domain, and then be multiplying it by that exponential. And so the operation of a system is really just modifying all the different exponentials inside of a function based off of h. And that's sort of calls back to an idea in 102. So that's pretty much the one of the main things that you learn just in this class in general is that you can take that result from 102 and put it back into here.
Yeah. So maybe you're confused about what the difference between the DTFT, DFT, and DTFS all is. I mean, well, first off, it's not a DTF, it's DFT. But also, corporate needs you to find the differences between the picture over here. Okay, now that you have proper time to appreciate the meme, let's get back to the material. So for the DTFS, it's basically a discretized Fourier series. So you take a signal, chop it up, and then you find the Fourier series of that chopped up signal. And it's only for periodic signals. If the signal is not periodic and is continuous, or I guess not continuous because you would chop it up. If it's not periodic, then you take the discretized signal and you take the Fourier transform of it, and it produces a continuous frequency spectra. This is the DTFT. And then for the DFT, it's basically the same thing as a DTFT, except you chop up the frequency spectra now into 2 pi over n points. So you can kind of think of it as like a circle. So what you're basically doing is you're taking the frequency spectra from let's say 0 to 2 pi, and you're chopping it up like even splits along the unit circle. Yeah. And then IDTFT, the time domain is periodic in nature because of the frequency domain is sampled. So basically, these are the relationships between the DTFT, DFT, and DTFS. So you can get from the DTFS to the DTFT by just extending the period to an infinite period to get the Fourier transform. And these are the same if they're periodic. And then you can discretize the frequency spectra to get the DFT, and you can reconstruct the DTFT if you chose the discretization according to the Nyquist frequency, which should be just greater than 2 times the Nyquist rate. So yeah. And if you want a visual for the how you chop it up, let me just exit here and I will show you guys the roots of unity. One sec here. Stop share. Roots of unity. So it kind of looks like this. You have a circle, right? And so this is like how you're chopping up the frequency spectra to get from the DTFT to the DFT. Is there any questions about this? Okay, moving on. And let's see, let us present. All right.
So
fourth
this
problem.
next problem is just going to be sort of motivating that last slide and thinking, okay, how are these things related? You might get a question that asks you to relate these things. They're pretty interconnected. Going through this problem shouldn't be too taxing, but it should definitely be hopefully illuminating on more explicitly just an example of how the three of them can actually be connected. And moreover, what you should see out of this is that if you choose your parameters right, the discrete Fourier transform and the discrete time Fourier series are not that dissimilar.
Yeah, if you guys are interested in quantum computing at all, there's a thing called the quantum discrete Fourier transform. It's pretty cool.
All right, do you guys want more time on this one? Nope. Cool. We'll keep moving forward. I'll say
to
briefly.
explain the answer?
Yeah. Nope. Great. I mean, this is really just oh, I just asked if we will be going over these at the end. We certainly can. You know, we're sort of trying to balance between giving you guys a chance to look at these before we go over them, and also, you know, having a recording. So, but we will go over them at the end. Don't worry. For all of the ones that you want to go back through, we can go back and look at them. Certainly.
Yeah.
Okay. So, go ahead, Cody. Sorry.
Oh yeah. So the DFT, the matrix form of the DFT is kind of like it's kind of like you versus the boy she tells you not to worry about, right? So this is like the formula for the DFT, versus the matrix form is like this, much more beautiful. Why? Because like you're gonna have to add up a bunch of random stuff for the non-matrix form, but for the matrix form you just have a predefined matrix and then you just do matrix vector multiplication. But if you hate linear algebra and just prefer to do sums, that's fine too. Basically the intuition is just you can arrange the x of k into a vector. So you have like x1 as your first value, and then x2, and then x3, and then x4, all the way down like as like a column vector. And then you have like the matrix, which are your e's, and then you have your another column vector like x to the n, where like it's like x1, x2, x3, so on. So you can kind of see this here as a matrix. So the omegas here are e to the negative 2i over n, and the matrix is just arranged like so. And yeah, and it follows something known as like modular arithmetic. So basically, you know that if you go around the circle once, right, then you're back at where you started. It's kind of like a similar idea. So like you have like 7, like mod 5, like you from your computer science class is like 2, I guess, right? Yeah. So this is a practice problem where if you use the matrix form of the DFT, it makes it really simple.
So yeah, go ahead and take a couple minutes to solve it. Again, probably just 5. And then we'll go through at the end. I should also mention that what Cody was talking about earlier with regards to the roots of unity is sort of how, you know, you can sort of conceptualize each of the columns as a form of that. Cody, it's sort of interesting looking back on all this while we're taking the algebra class.
Oh yeah, because the roots of unity is, if you guys are interested in theoretical math at all ever, the roots of unity also form something known as a cyclic group. So what that is like a cyclic loop is kind of like if you walk in a circle n times, you go back to where you started. That's kind of like what it describes, and that's what the roots of unity kind of describe too. And there are also solutions to x to the n minus 1 equals 0. That's where the name roots of unity comes from, because if you take them to the nth power, they all go to 1. So interesting
A good
little
way to
thoughts.
conceptualize how these transforms work. They essentially break down these signals into, these periodic signals, right? So almost like these things that sort of loop in on themselves. And then every single signal is sort of adding all these loops together in some weird way. And it's sort of the intuition that you try to get out of 102. And to me, it's a little more clear here because it's discrete. So as opposed to the size of these loops being sort of continuous, now they are sort of discretized, and you can start to see them a little more clearly how they add up. And then the action of a system is just sort of acting on each of those loops inside of an individual function, and sort of transforming the size of each of those loops and how that works. So
All right. Do you guys think you've had enough time to get through this? Or you guys need more time?
and we'll go through at the end.
Okay. So basically, first step is just to find the matrix version. So you should get something similar to this once you just like plug in to like the matrix form. And then you just do matrix vector addition. So you basically treat this as like a vector, and this is your matrix, and you matrix multiply to get your answers. How neat is that? All right. So windowing, so unfortunately, I didn't have the time to prepare a super in-depth discussion about windowing, but basically why you should care about it is that a computer can't read in an infinite length signal. So you have to cut your signal at some point and only look at the relevant parts. And a couple common examples are the Hamming and rectangular window. You might also see something called the Hahn window, so like HANN. And basically, there's like different advantages to choosing these different windows, but the main thing you will consider in choosing the windowing is how much information you gain or lose from the windowing, and also spectral leakage, where like if you take the DFT of the signal, you don't want the frequency peaks to smudge together. Like it's kind of like aliasing. If like you might have learned before, right? Where the different like peaks might like come together, right? When you take the Fourier transform. So you want to choose the windowing to avoid stuff like that.
All right. Now these last two problems are a little more conceptual. They don't they use more basic ideas of the DFT and DTFS actually. So go ahead and take a shot at them, and then actually, Cody, what we'll do, go ahead and flash this one up on the screen, and then flash the next one up on the screen. Okay. And then from there, I think we can actually stop the recording. So for everyone who is tuning in via the recording, hopefully we were able to give you some good intuition for solving these problems. A lot of these problems are going to be somewhat intuition based, and then just working through the math from there. So best of luck on your midterm.